Everybody, the next unit we're going to be doing is all about pressure, and we're going to go through the three different phases of pressure that we have here on Earth of solids, liquids, and gases. So I'm on page 344, which starts chapter 18. And a lot of times when you look at solids, you'll notice, especially in minerals, that they're made out of crystals. And we can sort of tell what the crystal looks like as far as its atomic makeup or its geometric makeup by looking at X-ray patterns of it. So if you look at this on the left-hand side, this is a sodium chloride molecule here. So I'm just going to put NaCl. This is table salt. So the green dots that you see, or green circles, are going to be the bigger chlorine molecules, and the white dots that you see there are going to be the sodium. Well, if you now look here at this X-ray pattern, you also have large white dots here. That's going to match up with the chlorine, and the smaller ones naturally will match up with the sodium. And so we can tell what the geometric design or how the atoms are connected together based on X-ray patterns. But the easier way, if you don't have our X-ray machine, is simply by finding the density of an object. Now, when you get density is basically how much mass of something there is in a given amount of space, and we call space volume. Okay, so it's mass divided by volume. Don't forget that we measured mass in grams, and volume is going to be measured either in milliliters or cubic centimeters sometimes. There's lots of different ways we can measure volume. But let's just take, and let's say you had a block, and this is one of the labs we're going to do. You're going to be given like 5 different blocks. And let's just say that block is, I don't know, 2 centimeters high. That's a 2, believe it or not. But it's really, really long. So let's make it 5 centimeters long. So it's 5 down here. But it's sort of skinny, so it's only 1 centimeter thick, like that. So this would be 1. Well, that means 2 times 1 is 2, times 5 is 10. So that just means that this thing has a volume of 10 cubic centimeters, if you can barely read that. Okay, so it's 10 cubic centimeters there that has a volume of. Well, if I wanted to find the mass of this, let's just say the mass was 100 grams. Okay. Well, to get the density, make this a different color. Density equals mass divided by volume. So I'm going to take that mass of 100 grams, divided by the volume of 10 cubic centimeters. We could also say milliliters, because a cubic centimeter and a milliliter are pretty well the same thing. And that gives you 10, 100 divided by 10 is 10, grams per cubic centimeter. Well, if I wanted to find out what material that was made of, I can simply look at a chart like you see over here. And if you look really closely, silver has a density of about 10.5. So I could possibly say that this block here, if it looks silver, had a lot of silver in it. Okay, so that's what we're going to be doing in lab. One of the things we're going to do is take a whole bunch of different years of pennies. We're going to find the density of each year. And the year that the density changed will be the year that they actually changed the metal. Many people think that pennies are made out of copper. Well, they're not anymore because copper is so expensive. So we changed the metal that they're made out of. And so one of the things you have to do in lab is figure out what it is. Now, also, if you look at page 347, the actual standard measure of density is called specific gravity. So if I can write that even more messy here, it'd be amazing. So specific gravity is sort of the formal name for density. And the way you do that is you take the mass of the object and divide it by the mass of an equal volume of water. So let me sort of explain to you what we're going to do here using what we just did. Let's just say that we had a mass of silver, which weighs 100 grams. Okay, 100 grams for the silver. Well, that silver was 10 cubic centimeters in volume. Well, 1 cubic centimeter of water, golly, I'm sorry guys, this is really having a hard time writing. That's supposed to be a cubic centimeter there. Gosh, that's 1 cubic centimeter of water is equal to 1 gram of water, which is also equal to 1 milliliter. So it's sort of nice with water is everything is one. You got 1 cubic centimeter, 1 gram, and 1 milliliter. So if I had 10 cubic centimeters of water, that means I would also put down here 10 grams of water, because 1 cubic centimeter is 1 gram per water. Well, if you look back up here, 100 divided by 10 is 10. And so therefore, the specific gravity or the density of water, of silver there is 10, okay? Or 10.5 if you look at the chart over here. So I don't really get hooked up too much on specific gravity since it's pretty well the same thing as density. On page 348, we're going to talk more about elastic limits. We actually already did that with Hooke's law when we did. Remember when we took the springs and we put weights on them and they stretched out? That was pretty well all about the elastic limit. But one thing that really is really important as far as an architecture, let me go to the next page here, is how we can make things lighter and darker and things of that nature. So if you look at the picture on page 350, you got this bar that has a huge weight on the right-hand side of it over here. And if you notice on the bar, the top part of the bar gets stretched out. See, it goes this way, it also goes this way, but the bottom part of the bar gets compressed. Well, if that's the case, if I actually stretched it out like it looks in your book here, let me see if I can do that for you. I'm just going to stretch this out a little bit. If you notice, the actual inside of that dotted line doesn't really curve all that much. So therefore, there's not much strain in the middle part. Okay, the middle part doesn't have to be all that strong. So when engineers actually design things, here's what they do. They make it eye-shaped like you see over here on the right-hand side. The top part, it has to stretch a lot. The bottom part, so this part here stretches if you look over there on the left-hand side. This part down here compresses if you look over on the right-hand side, but the part in the middle doesn't have to do much at all. So therefore, they can take a lot of the steel and save a lot of money by just making it a lot lighter, but it's the same strength because the middle part here doesn't go either way very much. It doesn't compress, it doesn't stretch. So you can get the same amount of strength with an I-beam as you would with a solid block of steel. It's a lot cheaper, plus it's a lot lighter, so you don't have to support as much weight. Okay. If you look at these bridges down here, and I'll do this little lab, demonstration lab. If you notice, there's a lot of triangles. So triangles and arches are great shapes to support things. In fact, I'm going to have you hold an egg in your hand and try to smash it with your hand by squeezing it. You will not be able to do that. So this is often the shape here that they have is on page 352. And once again, it's sometimes called an arch or a catenary, or however you want to say it. So there's a very, very, very strong shapes here. It's because it's natural support of supporting something left and right and also back down to the base. Finally, one of the most important parts of this chapter is how we measure strength, or they call it scaling. And I just want you to look at these blocks here, the fact that if you take the length, whoops, get my pen rolling here. I'm going to take the length, what we call the area of it, and then also the volume of it. Well, if you have something with a length of 1, its area is going to be 1 squared, which is still 1. Okay, so 1 squared is 1. The volume would be 1 cubed because it's base times width times height. So that's also 1. Now watch what happens though if you start doubling this. If the length was 2, now you're going to have also the length would be 2 on all the sides, but the area is now 2 squared. So 2 squared would be 4. It's not 2 times 2. Well, it is 2 times 2 in this case, but we'll get into that in a minute. And then finally, the volume is going to be 2 cubed because it's length times width times height. So now the volume is going up much, much faster than the area. Okay, look. So the area just doubled the side. The volume is going to be the cube of the side. So if it was 3 times as big, if each side was 3 times as big, the length would be 3 again. The area is always the length that it increased squared. So 3 squared is 3 times 3, or 9. But watch what happens to that volume. That volume is 3 cubed, which is 27. So if you notice, the volume here is always rising much, much faster than the area. Now that's going to be really, really, really important when we deal with strength. So the way we look at the strength of something is actually by taking its surface area. Oh, wait, I am so sorry that this looks so messy. That's actually an N, believe it or not. Strength is going to be the surface area to volume ratio. So watch what happens here. On the first cube over here, if you notice, the surface area was 1. The volume was 1. So let's just say it had a surface area to volume ratio of 1. Now, watch what happens as you get bigger. As the surface area doubled, remember if you look right over here, when the surface area doubled, wasn't the surface area 4? But watch what happens to its volume. It's now 8. Well, 4 divided by 8 is 0.5. So since we're measuring strength by surface area to volume, as the surface area gets bigger, its volume gets bigger faster. So actually 0.5 is less than 1, so something that's bigger is weaker. Now, let's look at the third one here. The third had a surface area of 9, but its volume was 27. So now you went down even lower to 0.3. So every time something gets bigger, it actually gets weaker. And that's why things like an ant, well, you might not think an ant's as strong as an elephant, but an ant can lift many, many times its body weight. So in a way, it's a lot stronger because an elephant could not lift its body weight. Okay, even though it can lift many more pounds than an ant, it couldn't lift many times its body weight like an ant could. So in physics, we often consider strength to be the surface area divided by the volume. And since volume increases faster than surface area, the bigger something is often the weaker it is. That's why when my daughter was in gymnastics, it was just amazing to me that these what I call short or small young ladies, and also the small young men, could do such strong tricks. And in gymnastics, it was just really, really phenomenal to watch them. If you look down here, here's an elephant here. This is an African elephant. You can tell by its ears because they look like Africa. And just to sort of give you a great example, by the surface area here, an elephant could not lift its own body weight. Here's a little trivia fact about its ears, though. They use their ears for cooling themselves down. And remember this from last chapter, evaporation is a cooling process. So when they spray water on their back, they then flap their ears. That creates a wind current for evaporation and then cools the elephant. Also, there's a lot of blood in the elephant's ears, so that allows them to cool down fast. So just a little trivia there. All right, so as long as you've got surface area to volume ratio, we'll do the labs as soon as we get to class, and just make sure you got all these notes down, and I'll check in when we get to class. Have a great day. Love ya. Bye.